So this video is the next example that we have for Newton's law of cooling. And here's Newton's formula. And you may be looking at it and go, well, that's not exponential. Well, if we take t minus ts and we make it this, now it is. So this is now our new law of cooling. And this is the one that we're going to be using. So this is the derivative, which will tell us the rate of change in temperature. And this is the one that will give us the exact temperature at that time. Well, approximate. Okay, so we have a relevant example here. A freshly brewed cup of coffee has a temperature of 200 degrees. So it's freshly brewed, and you obviously can't drink that. It will burn your mouth. The room is 78 degrees Fahrenheit, and we're saying it took 14 minutes for the cup of coffee to reach 150. Okay. So now what we're going to do is use Newton's law of cooling to create a function that gives us the temperature in degrees Fahrenheit of the coffee in terms of time t minutes after it's brewed. So what we're looking for is we want to get this down to a temperature that we can actually drink it. So how long will that take? So we've measured the temperature, 200 degrees initially, and then it took 14 minutes for the cup of coffee to reach 140. So what is TS? TS is our stable temperature. This is our room temp. And what T0 is this is our initial temp. And K is our proportional constant. And it's affected by things like what we're cooling through, surface area, other things like that. So we've already taken our experiment now and we can plug these in. So our T here is TS. So that would be 78 degrees. So that's basically the temperature of the room. And the way you want to look at it is we're taking this temperature and we're adding to it the difference in the coffee. So our T sub 0 is 200. So if we plug that in, it's 200 plus 78 e to the kt. I mean minus, it's our difference. All right, so if we plug that in our calculator, 200 minus 78 is 122. And so that is the difference in our temperature. No more degrees here. So the way you can look at it, is that it's 78 degrees, that's the room temperature, plus what the coffee is adding to the temperature. Okay, so this is our formula, and so to really quickly check it, remember if you plugged in 0T, that'd be 122 plus 78. Everything works great. So now we can take our stuff, what we already know. So if 14 minutes go by, our temperature is going to be 150. So we can plug that in. T of 14 equals 150. So 150 equals 78 plus 122 e to the k times 14. And then we subtract the 78 over, which gives us 72 equals 122 e, and I'm going to write now 14k. And then there's our exponential. So all we have to do now is solve that. So 72 equals 122 e to the 14k. Okay, good. 122, 122. Plug it in the calculator to reduce it a little bit or leave it alone. We're going to plug it in anyways. And then now natural log to both sides. So we get 14k equals ln 72 over 122. Divide by 14, divide by 14. Plug it in the calculator. So natural log of 72 divided by 122. And so we now get negative 0.037, and we'll do 7, 4 decimal places. So 377. All right, negative 0.0377. And that's our K. So now if we plug that in, we have a formula that will give us the time it takes or the temperature at a certain time. That. And so now all we have to do is verify it to make it sure it's true. So at 14 minutes it's supposed to be 150. So we already know if we plug in 0, this is 200. So now let's make sure that it works the other way as well, as it's cooled. And you can see it came out negative. That's exactly what we wanted, because our temperature is decreasing. So now if we put in 14 minutes, we get 150 degrees. So it checks perfectly. So now we can use this to find out what temperature we want. So we want our temperature to be 140 degrees. So we're going to say T of we don't know equals 140. That's what we're looking for. So we're looking for time. So when you make a formula, you always want to make sure you put everything in what they are. T is the temp after time t, and it is in degrees Fahrenheit. And T here is time, and that's in minutes. We could probably just put those in parentheses like that. Okay. So if we do 140 degrees, that's 140 equals 78 plus 122 e to the negative 0.0377 t. And so it's exactly the same solving as we did for k, except now we're solving for the time. So we subtract 78, so 140 minus 78 is 62. Divide by 122. I'm going to put the e now on the other side. Oh, who cares? We'll just put it on the other side. Let's plug it in the calculator. 68 divided by 122. Math, fraction, enter. 34 over 61, or we can use 68 over 122. They both work. But 34 over 61 equals, a little dotted line, e to the negative 0.0377 t. And then natural log. So obviously it should be more than 14 minutes, because 14, it was 150. So now a quick divide, and we're done. So now we'll take that number and plug it in our natural log. Go up and grab it, enter. Divide it by our rate, which is negative 0.03, and I could just go up and grab it and bring it down. But I'm going to use my decimal. And there it is, so 15.5 minutes. So if you wait 15.5 minutes, you can drink your coffee. So next question is, when will the coffee's temperature be decreasing at a rate of? And this means we're looking for T prime. We're looking for the derivative. We're looking for the change in temperature per time. See, it's degrees Fahrenheit per minute. So we're going to take the derivative with respect to time. And you can just go back up and use this. You can see that it's just that part with k, right? So we're just going to basically put the rate in front. But we're going to take the derivative just to be mathy. All right, so the derivative, let's write t down first. Let me zoom in and write t. So t equals 78 plus 122 e to the negative 0.0377 t. All right, so we take the derivative. The first number is a constant. It's gone. And then remember, with exponentials, we just rewrite it. And then it's times the derivative of the exponent, which is our rate. It's our k. So you can see that's the formula. See? It's just k times our formula itself without the 78. Okay. So now we can take t prime equals, and I'm going to take this one and multiply it to 122. So 122 times negative 0.0377, just to make a nicer formula. So negative 4.59, so just 4.6. Sounds good. All right, and there's our formula. So now if we plug in we plug in 2 degrees Fahrenheit per minute, that's our derivative. So our T prime equals 2 degrees Fahrenheit per minute. If we plug that in, it will tell us when the temperature is decreasing at that rate. Kind of a weird question, but it's kind of cool too. All right. So now if we take 2 and divide it by negative 4.6, we get negative 10 over 23. And yeah, I'm going back and forth here. We're looking for the math behind this, not the significant figures. All right, so now you may be looking and going, oh, wait a minute, there's a negative here, and that's a negative. So when I do a natural log, it's not going to work. This is why paying attention to the question is very important. It says it is decreasing. That's negative. So it's negative 2, which turns this into a positive. See, very important, that little decrease part. One makes it bigger, one makes it smaller. So yeah, it's a huge difference. Okay, so now that cancels and we end up with ln of 10 over 23, and then again it's just going to be divided by. It's the same steps, 0.377 equals t. So now if we plug that in, it'll tell us when the rate is decreasing by 2 degrees per minute. So natural log, go up, grab that, but I have a negative, so I'm going to put times -1 to get rid of it, and then divide it by -0.0377. so just say 22 minutes. So at 22 minutes, our temperature is going to be going down by 2 degrees per minute. So what that means is if you were to plug in 22 into our function, like this, you get 131 degrees. So what are we expecting? We're expecting a 2-degree temperature drop. So at 22 minutes, the temperature is 131. So we're expecting at 23 minutes for it to be 129 degrees. Still drinkable, still going to taste good. But there you go. There's every single question now that we could be asked with exponential functions to find.